Hi, my name is Anaya Boyce, and today we're going to talk about something that we all do but never talk about. For our example, we're going to be looking at a one-way ANOVA, and remember, a one-way ANOVA has one factor with a minimum of two variables that are independent. We're actually going to be doing a hand calculation to show the simplicity of the one-way ANOVA. So the data is in, it's clear, we all pee in the shower, okay? The question is, does the condition of the shower determine how much we pee? And that's what we're going to look at in our study today. We have 7 individuals in each group, and we're going to look at 3 groups with different conditions. So let's look at our 3 conditions. The first condition is the no water condition. It's a normal shower. The only difference is we have a wet rag or wet cloth that we're going to allow the individual to bathe with rather than running water. Our second condition is a cold water condition, and this is where they have all the regular amenities of a normal shower, but the only difference is that the shower water must be cold, and that's lower than body temperature. The third condition is the final and probably the most comfortable condition, where the individual is allowed to bathe with regular warm water. So we're going to eliminate any confounds by allowing individuals to the comfort of their own home and their own shower. So we're going to avoid any kind of shy bladder syndrome that would allow an individual, if they know researchers are watching, to be shy when it comes to regular bathing. We're also going to put a mechanism in the drain of the shower that detects urine so that we know when an individual pees in the shower. So throughout the week that we're going to be looking at the amount of times an individual pees in the shower, our hypothesis is that the different conditions are going to determine that there are different amounts that an individual will pee in the shower based on the condition. The more uncomfortable the condition, the less an individual will pee, and the more comfortable the condition, the more an individual will pee. So our null hypothesis is going to be that there's going to be no difference in the rate of urination based on the condition. So our independent variable would be the water condition, and our dependent variable will be how many times a subject urinates in the shower. So for our calculations, the number of levels or the factor is going to be represented by A. N is going to be the total amount of participants in our study, and N is going to be the number of participants in each level, which is 7. And we're going to use an alpha level of 0.05. So the first thing we're going to calculate for our study is the degrees of freedom. So we're going to do that for between, within, and then the total. For between, we're looking at A minus 1, which is 2. For within subjects, it's going to be N minus A, which is 18. And the degrees of freedom for the total is going to be N minus 1, which is 20. We can use the 2 degrees of freedom, 2 and 18, to determine the critical value using an F table. So on our F table, we're going to line up our degree of freedom of 2 at the top and our degree of freedom at 18, and we're going to land on 3.5546. And so we're going to determine, our decision rule is going to be, if F is greater than 3.5546, we're going to reject the null hypothesis. So this chart represents the 21 individuals, their 3 conditions, and the amount of times they urinated. So what we're going to do to calculate the sum of squares is we're going to sum the squares of all the groups, we're going to square them and add them together. So for the first calculation of the sum of squares, we're going to calculate the sum of square for between subjects. And we're going to take the sum of each level, we're going to square it and add it together and divide it by the number of subjects in each level. Then we'll subtract it from the total sum if all the numbers were added together, squared, and divided by the sum of the total number of subjects. So you can see the equation that we have here, where we take 57 squared, 47 squared plus 21 squared, divide that by 7, minus the total, which is 125 squared, divided by 21, and that gives us 98.67. For within subjects, we're going to have to find the sum of all y squared. So we already have the sum of all categories squared, which is 57 squared plus 47 squared plus 27 squared. So we're going to plug that into our equation and find y squared, which is all the values squared and added together. And when we work out this calculation, that's going to give us 10.29. So that's going to give us our sum of squares within subjects. For this total sum of squares, we have our y squared, and we also have our total. So we plug in 853, which is all sum of y squared, plus the total number of subjects squared, 125 divided by the total number of subjects, which is 21, and that gives us 108.95. So now that we have our sum of squares, we can use them to determine our mean squared. If f equals mean squared between divided by mean squared within, then we can plug them into the equation. So mean squared between equals 98.67 divided by degrees of freedom, which is 2. Mean squared within is 10.29 divided by the degree of freedom of 18. And that works out to 49.34 divided by 0.57. So f equals 86.56. And so we determined if f is greater than 3.5546, then we're going to reject the null hypothesis. 86.56 is greater than 3.5546, therefore we're going to reject the null hypothesis, and the urination rates differ significantly based on water condition. So to wrap up, in conclusion, we determined that if f is greater than 3.5546, we're going to reject the null hypothesis. F is equal to 86.56. Therefore, we reject the null hypothesis, and we now know that not only does everyone pee in the shower, but the temperature and condition for the water determines just how much we pee. Thank you.